Welcome everyone to this deep dive explainer on Oops with Java, specifically focusing on Unit 5. Today, we're going to completely unpack the Spring Framework and Spring Boot. We're skipping the basic fluff and jumping right into the deep end. Whether you're prepping for those grueling university exams or getting ready for a massive technical interview, we're going to break down these enterprise-level concepts step by step. I want to make sure you're not just memorizing the how, but really truly understanding the why under the hood. So let's get started. Here is a quick look at our roadmap for today's explainer. We'll start with an intro to the Spring Framework, then dive into inversion of control and dependency injection. After that, we'll look at Spring Beans and their lifecycle, touch on aspect-oriented programming, build out some RESTful Web APIs, and finally, wrap it all up with Spring Boot fundamentals. All right, Section 1, Intro to the Spring Framework and the historical context behind it. To really master Spring, we have to understand the exact headaches it was actually built to cure. You can't appreciate the fix if you don't know what was broken. So let's trace the evolution of client-server programming. Back in the early days, we relied entirely on static HTML. These were basic web pages that looked exactly the same every single time a client requested them. Pretty boring, right? Well, as demands grew, we obviously needed dynamic content. This brought us Java servlets and Java server pages, which allowed developers to actually write server-side code to interact with databases. But let me tell you, hard-coding raw SQL queries right inside your Java code was a nightmare. It was incredibly tedious. Enter Hibernate and Enterprise Java Beans. Hibernate was a huge step forward because it mapped database tables directly to Java objects, removing those messy SQL dependencies. But configuring them, still ridiculously complex. Finally, the Spring Framework came onto the scene. It was a game changer. It's essentially the ultimate framework of frameworks. A unified, lightweight solution that takes all those earlier technologies and bundles them into one robust, manageable package. Now, let's peel back the layers of Spring's architecture. It is beautifully modular. Right at the foundation, we have the core container. This is the bedrock that handles inversion of control and dependency injection. Sitting right above that is the data access and integration layer, managing your database connections, object relational mapping, and crucially, transactions. Think about a bank ATM for a second. If you try to withdraw cash and the machine completely crashes right before the money comes out, the system absolutely has to roll back that database change automatically. This layer guarantees those ACID properties: atomicity, consistency, isolation, and durability. It ensures your data integrity is bulletproof. We also have the web module powering the model view controller architecture, plus the AOP and testing modules, complete with JUnit support to ensure your enterprise code is clean and bug-free. Moving right along to Section 2, Inversion of Control and Dependency Injection. This is the core engine that makes everything run. So, what is inversion of control, or IOC? This is the defining characteristic of Spring. In standard Java programming, if your code needs an object to do something, you manually build it using the new keyword, right? You are micromanaging, you are in total control of that object's life. Well, IOC completely flips that script. You are surrendering the control of object creation and its entire management over to the Spring Framework, specifically to the Spring IOC container. The framework is now the one calling the shots and dictating the flow of the application. And here is the so what of it all. IOC fundamentally shifts our entire code architecture from tight coupling to loose coupling. Tight coupling is when your classes are heavily dependent on one another. It's like a house of cards. You change one class and you're forced to rewrite 3 others just to keep the app from crashing. It's a highly fragile system. Loose coupling, on the other hand, gives you highly independent modular components. Because the Spring container is managing the objects, your classes don't need to be hard-coded to rely on specific external stuff. Why should you care? Because when your boss inevitably bursts into the room asking for a massive new feature by Friday, loose coupling means you can plug it in without breaking the entire application. It makes enterprise apps vastly easier to test, maintain, and scale out. But how does Spring actually pull off this inversion of control? It uses a clever design pattern called dependency injection, or DI. With dependency injection, an object doesn't have to go hunting around the system for the external resources it needs to do its job. Instead, the Spring Framework actively passes, or injects, those required dependencies straight into the object at runtime. You basically just put up a flag saying, hey, my class needs X, Y, and Z, and the framework drops the fully assembled objects exactly where they need to be. Okay, let's jump into Section 3, Spring Beans and their lifecycle. Let's look at the actual components. I always love this simple analogy. Just like coffee beans are the core ingredient for a great cup of coffee, or a cup of Java, if you will, Spring beans are the foundational building blocks of the Spring application. But let's demystify the term. A bean isn't some magical entity. Technically speaking, it is simply a regular Java class object, often called a plain old Java object, or POJO, that happens to be instantiated, assembled, and entirely managed by that Spring IoC container we just talked about. Now, when the container creates one of these beans, it assigns it a scope. This scope dictates exactly how long the bean lives and where it can be seen. There are 6 primary scopes you need to know. Singleton is the absolute default. The container creates one single shared instance of that object for the entire application to use. It's highly efficient. On the flip side, prototype scope generates a brand new instance every single time the object is requested. Then we have 4 scopes specific to web applications. Request scope lasts for just a single HTTP request. Application scope is shared across the whole web context. WebSocket scope is tied to an active socket connection. But let's pause on the session scope for a second, because it's crucial. Imagine a user logging into a secure banking portal. The framework essentially hands them a unique secure locker, a session ID. Every piece of data specific to that user lives in that locker for the exact duration of their login. The second they log out, the session scope terminates and that locker is wiped completely clean. Of course, we have to actually tell the framework how to manage all these beans. Traditionally, this was done using XML configuration. And let me tell you, it meant scrolling through miles of verbose, error-prone XML files, manually setting up explicit bean tags. It was flexible, sure, but brutally tedious. Fortunately, we don't really do that anymore. Today, the standard is annotation-based configuration. Instead of writing separate, massive XML files, you just drop an annotation, like @component, @service, or @repository, right above your Java class. It is incredibly clean, modern code, and it drastically cuts down on your configuration overhead. And building right on top of annotations, we get an absolute powerhouse of a feature, auto-wiring. Using the @AutoWired annotation. This little tag tells Spring, hey, scan the application context, find the exact collaborating bean I need, and inject it right here. No explicit manual wiring required. Now, a pro tip for you. While you can auto-wire fields or setter methods, injecting those dependencies directly into your constructors is widely considered the safest, most reliable best practice in modern enterprise development. Definitely keep that in mind for your interviews. To keep all of this organized, every single Spring Bean goes through a very strict 5-step lifecycle. It's a predictable pipeline. Step 1 is instantiation. The raw object is born in the container. Step 2 is populate properties, which is exactly when that dependency injection we just covered actually happens. Step 3 is initialization, where any custom setup or initialization callbacks get triggered. By step 4, the bean is fully baked and ready for use by our application. And finally, step 5 is destruction. When the application shuts down, the container safely cleans up and disposes of the object to free up memory. All right, moving into section 4, aspect-oriented programming. Now, standard object-oriented programming is great. It breaks our code down into classes. But aspect-oriented programming, or AOP, takes that modularity up another level by decoupling what we call cross-cutting concerns. Let's break that down. Think about application logging, security authentication, or transaction management. You need those tasks happening everywhere across dozens or hundreds of different classes. Without AOP, you'd be copying and pasting that same security check logic thousands of times. It's a maintenance nightmare. AOP lets you strip all that out. You write the security logic exactly once as an independent aspect, and the framework automatically applies it or weaves it across your entire application wherever it's needed, while keeping your main business logic completely uncluttered. Let's shift gears to Section 5, Building RESTful Web APIs, focusing on the web layer. Up until now, we've been looking under the hood at the internal app. Now we need to scale up and connect our robust Spring application to the outside world, mobile devices, browsers, you name it. To do that, we build RESTful Web APIs. REST stands for Representational State Transfer. It runs on some very strict principles. First, a clear client-server architecture. Second, stateless communication, meaning every single request is independent and the server doesn't remember your previous request. And third, a uniform interface. Think about how a company like Netflix or Uber maintains one single centralized database, but seamlessly serves a desktop browser, an iOS app, and an Android app all at the same time. The secret sauce is REST APIs. The centralized server exposes endpoints, and all those totally different client devices talk to those endpoints using universal, lightweight data formats like JSON or XML. And the way these clients communicate over a REST API is dictated by standard HTTP request methods. Conveniently, these map perfectly to your standard database CRUD operations: create, read, update, and delete. A GET request maps to a select or read in the database. It is safe, meaning it retrieves data without altering anything on the server. A POST request, however, maps to insert or create. You are actively submitting brand new data to the database. It is absolutely vital that you keep the distinction between GET and POST crystal clear. Moving down, a PUT request corresponds to an update, which replaces an existing resource entirely. And lastly, naturally, a delete request removes a resource from the database. So, we've covered a ton of ground today, but it actually brings up a really critical question. If the core Spring framework is so incredibly powerful and modular, why does the entire industry constantly talk about needing Spring Boot? What's the missing piece here? Which brings us to our final segment, Section 6, Spring Boot Fundamentals. This is the modern standard for Java development. Here is the reality. The standard Spring framework is immensely powerful, absolutely. But manually configuring all those modules, wiring the databases, setting up the web servers, managing the XML, it can literally take days of repetitive boilerplate work before you even write your first line of actual business logic. Spring Boot completely cures this headache. It provides an auto-configured, highly opinionated, ready-to-run package that even includes a built-in web server. But to start a boot application, you have to pick a build system to manage your libraries and dependencies. You've got two main choices, Maven or Gradle. Maven relies on a highly structured XML file called pom.xml. It's a bit rigid, but it is universally understood across the industry. Gradle is the newer, increasingly popular alternative, especially if you ever dabbled in Android development. It uses a build.gradle file written in a flexible, task-based, domain-specific language, which gives you way more customization if you have complex build requirements. Once you're set up, maintaining a clean directory structure within your Spring Boot project is paramount. Boot enforces a beautiful separation of concerns, and it generally looks like this. At the bottom, your model or entity layer maps directly to your database tables using the @entity annotation. Right above that, the repository layer handles actually querying those tables, marked by @repository. Above that is your service layer. This is the brain of your application. It processes all the complex business rules and validations using @service. And finally, sitting at the very front is the controller layer. Tagged with @REST controller, it acts as the traffic cop. It takes the incoming HTTP web requests from the user, asks the service layer to process them, and then returns the proper REST response, like a JSON payload right back to the client. Wow, we have covered an immense amount of theoretical ground in this explainer today. We've gone from the historical pain points that made Spring necessary, all the way through the granular mechanics of dependency injection, bean scopes, AOP, REST APIs, and finally, Spring Boot architectures. But the true test of all this knowledge is application. Now that you've mastered the underlying mechanics of this incredibly powerful engine, I want to leave you with a challenge. How will you leverage Spring Boot to build your very first enterprise-level application? Take all this theory, open up your IDE, and just start writing code. You've got the tools now. Thank you so much for learning with me today, and best of luck on your exams and those upcoming interviews.